So thank you, the organizers, for organizing this conference. I have learned so much about the CGM, which I somehow missed. Many of the papers were presented, which are very exciting. What I would like to do today, basically continue from where Rob left off, and start by inviting everybody to think more about the CGM at high redshift. I would like to posit that since the launch of JWST, the game has changed. Before that, it was almost impossible to think about doing detailed spectroscopic surveys at high redshift. But right now, it's becoming routine. Just like the FRB field, the introduction of JWST has proliferated the way we can do CGM science at high redshift. We can, simply because we can do better spectroscopic surveys. Now, this is a simulation rendering of illustrious TNG, and this is sort of the picture we have in mind today when we talk about CGM, primarily because of all the landmark studies that have been done for the last 10, 20 years. CGM primarily is sorry, that was not intentional. The galaxy is pretty much in the center of a dark matter halo. The CGM is loosely defined, again, people might quibble, but loosely defined as this diffuse halo gas, which is filling the dark matter halo and loosely bound to the gravitational potential well. That's the broad definition, okay? And remember the scale here. It's filling the dark matter halo at redshift 0, so it'll be like 300 kiloparsec in radii, etc. But if you go to high redshift, the picture is different. As Rob alluded, if you look at, again, a snapshot of a simulation, galaxies have not formed, okay? Galaxies are tiny, and more importantly, look at the prediction from simulation, assuming we believe the models. The gas is filling, oops, I don't know what's going on. The gas is filling the large volume around the galaxy, which is well beyond the dark matter halo. Also, look at the ticker. The sizes are very small. So the question I would posit is there something like a canonical CGM at high redshift that we see at low redshift? And we basically thought that was a good enough question that we can invest large amount of JWST time to it. So the survey design roughly is around 6 high redshift quasars where we are doing near-cam slitless spectroscopy. It's a huge investment of resources, more than 100 hours of near-cam spectroscopy with free imaging that comes with it, 100+ hours of ground-based spectroscopy with different spectrographs, and 50+ hours of imaging and IFU observations for these fields. And the main science questions we want to address are not just the CGM science, which I'll allude to today, but we want to understand how cosmic reionization happens, because this is the late stage of reionization. We want to study how the supermassive black holes form. We also want to understand how galaxies interact with the inter and circumgalactic gas. Basically, define the early cosmic ecosystem. That was one of our motivating goals. And because it's a slitless spectroscopy, so we have to be slightly clever how we design our experiment. So in NearCam, there are 2 modules, okay? One module will disperse the light in one direction. The other module will disperse the grism light in the opposite direction. We can use that to actually deblend lines which might otherwise overlap in slitless spectroscopy. And we can actually do a dithering pattern so that if you set the quasar in the center, in a central region of around 300 kiloparsec, we have the most exposure time in this setup. This image, again, I'm just showing up again that Rob showed, is the redshift 6.33 quasar here in the center. And you have an image which is around 3 times 25 arc-minute square on size, which is around 3 times larger than the Hubble Ultra Deep Field and deeper than that. Okay? That's not the fun part here. We have spectra of galaxies which are at magnitude of 28.5 AB. That's ridiculous before JWST. And that allows us to really probe very, very deep and study, as Rob has shown, very faint galaxies at high redshift. I just want to take a few seconds to show you the data because I'm an observer and I'm very proud of the data we collected. It was a pain to actually set up the procedure to actually analyze the data. So this is the kind of, not really raw, the first reduced image you'll get from slitless spectroscopy. You get a lot of broad emission lines. So you have some very, very faint, narrow emission lines shown here. And then you have to model out by modeling the continuum of these lines. We can subtract the continuum out to see only where the emission lines remain. And knowing the wavelength solution, we can actually identify what these lines are. For example, these two lines are O3 emission lines at redshift 6.33, and we can actually do a transformation. These detector positions correspond to an array deck on the sky, and we see that, lo and behold, there is indeed a galaxy. Similarly, for these lines, we see that there is H alpha and sulfur 2 line. For that position, there is another redshift 4 galaxy. You might notice that the O3 lines are shifted in the two modules. As I mentioned, this is one of the key features, okay? Both the gratings are dispersing the light in the opposite direction, so if you are not centered on them, your lines are not going to align. And that's a good thing, because I want to know where this H alpha galaxy is, where the redshifts are, and it's exactly aligned. Whereas there is a contaminating line coming from some other galaxy, because it's slitless. And we know that this is contaminating because it's not showing up in the other module. That allows me to actually study single emission line galaxies also and characterize their redshifts accurately. So this is a trick we use, and go and analyze. And what I'm going to focus on mainly are the results from our first field of the JO100 field. In the first stab, we already got, as Rob showed, around 117 spectroscopically confirmed redshift 6 galaxies around a quasar. These galaxies are clustered. Some of them are behind the quasar, some of them are in front of the quasar. I'm not going to go into the detail. I'll just tell you a little bit about what other science we can do beyond CGM. One thing we can do, here I'm showing you the near-infrared spectrum of that quasar itself. Here is the optical part of the spectrum, and you'd see this is the Gunn-Peterson trough because it's a quasar at redshift 6.33. What I would allude to you are these little spikes you see here. These are transmissions, Lyman alpha transmission spikes at high redshift. These primarily correspond to zones where there is less neutral hydrogen at high redshift. That's all. The question we ask is there a cross-correlation of where the position of these transmission spikes exists with galaxies themselves? You can look at Lyman alpha and Lyman beta transmission. Because they are not emission, rather lack of hydrogen. Of course, Lyman beta would be stronger than Lyman alpha. And then we just look where the galaxies are. And then do a cross-correlation analysis and ask the question, what is the average transmission over the mean transmission on the y-axis? So my mean transmission is 0. Whatever is x-axis is the average transmission you would see as a function of co-moving radius around galaxies. So I would draw your eyes to the blue line here. You see this excess spike? That's a signature of the reionizing bubble where there's excess transmission. The fact that you have nothing here just tells you that very close to the galaxy, basically it's all dense gas. This tells us that we can characterize the size of the bubble to be around 5 co-moving megaparsec. All right, so then we can move on and try to understand what's going on for the CGM of galaxies very close to it. For this, we have to look at the central part where we have single emission line galaxies, which when we try to identify, we find additional 74 galaxies. And if I focus very close to the quasar, I have around 29 galaxies. And this is the sample I used to study what is going on in the CGM traced by magnesium to absorption. And the workflow is as follows. I have a very beautiful quasar spectrum. There happened to be a strong magnesium to doublet, you can see here. We can find an associated galaxy exactly at that redshift, and we do the cross-correlation. Same game. Here I'm showing you, on this axis, the equivalent width of the absorbers. On the x-axis, whoa, it's going crazy. On x-axis, the impact parameter. And I would draw your attention to the points with the shaded circles, which are the galaxies closest. Okay, there is an environment effect, I'm not telling you. And at first look, you would see that, oh, this has an inverse correlation, as you'd expect, and this dashed line is what you'd expect at redshift 2. So it seems like there is no difference, but the galaxies are much smaller. So if I normalize them by their R200 or their halo masses, effectively you see that the galaxies are tracing the CGM gas all the way up to around 8 R200. So they extend much further out than you would expect at low redshift, where it goes to only around 0.7 RVR. I'm going to skip that, and I want to make my main point. We also look at the kinematics of the gas, and Using the kinematics of the gas and comparing it with the galaxies, I can make this plot. On the y-axis, I'm showing you velocity normalized to escape velocity, x-axis, again, the distance. And you'd see that all the objects within this circle is bound, in this square is bound, everything is unbound. And most of the gas is consistent with being unbound to the dark matter halo of these CGMs. You can look, there is a lot of environmental effect and decay standing there, so I'm going to skip that. And let me just make one final statement here, that we are conducting a full survey where the 6 fields are now in, which will extend the CGM survey we have to around 200 galaxies, which corresponds to 946 O3 emitters and around 1,500 H-alpha emitters in total. Okay? Combined all, we'll have a sample of around 200 galaxies, which will allow us to trace the CGM. I'm going to skip that, and basically enable us to constrain what's going on at high redshift with much further accuracy. With that, I'll stop. The two main things I want to say is, again, JWST is an extremely efficient tool for CGM studies. Think about it. And second is that the CGM at high redshift is dramatically different than what we see at low redshift. All right, I'll stop now.
Thanks so much, Rongmon. Some questions? Go ahead.
So these are EOR galaxies. So and you're looking at gold gas. So do you have a sort of sense of these ionizing cones or anything? Can you correlate like maybe oxygen to oxygen 3 ratios or star formation rates, surface densities that people have sort of used as proxies of leakage,
Yes.
Lyman-Kitchener leakage?
So we don't have O2 simply because of our wavelength coverage. We have O3 H beta. So there are constraints in one of the previous papers about what is going on in the ionization budget. But I showed you in this figure, like we showed you that if you do a cross correlation with Lyman alpha transmission, there seems to be a coherence length of around 5 co-moving megaparsec. That's the bubble size, sort of zone of influence around these galaxies on average.
Another question, and we'll get William set up also. So back here and then up here.
So, sorry, with the GRISM spectra, can you characterize outflows?
Yes.
The broadening of the lines?
Yes, it is possible.
What do you
That's
see?
So we do see definitely they're broadened. That paper is not published yet, but it's a little bit harder because you don't see the continuum, right? So you can stack and do a statistical measure. We definitely see broadening. And for most of these objects, there is an outflow that's being driven. For some individual cases, you can definitely see blue shifting, but not for all.
Real quick right here.
So these kind of galaxy can be seen by ALMA?
Excellent question. Well, first of all, ALMA doesn't have such a big field of view, but some of them you would be able to pick up for sure. Yeah, but nobody has done such a big survey so far.
All right, let's thank Rongmon again.